let's study B plus trees, right. So, we have seen B tree. In this B tree, we say that you will have a node here, it will contain one element and its children can contain one or two elements like this. It can contain some elements like this 4, 5. Its children can contain 3 elements because this is, since it is containing 2 elements, that is 2 keys, its children can contain 3 elements. So, 6, 7, 8, and the important rule is the element inside each node are in sorted order. Okay, we are trying to reduce the height of the tree with this B tree concept. Okay, but still, if I just go back to the B tree diagram here, see, if I want to insert a new element, or if I want to traverse, or I want to delete an element, you have to do lot of operations, right? You have to do lot of operations, right? Why? If you want to delete, suppose you want to delete 65, okay, we cannot delete 65, we can delete a node only, right? So, if you want to remove this 65 and replace with some element here, okay, you want to replace with some element here, right? So, it is an hectic process, finding out the node, traversing, finding out which one to replace. We have seen already this, how to do, even in just the recent one, that heap sort we have seen. In heap tree, we are always heapifying. Once the element is deleted, we are doing lot of process there, comparing, sorting, comparing, swapping, you are doing lot of changes, right? Even in B tree, that problem exists. Right. So, even in B tree, we are doing lot of operations here because it is following BST logic. So, check it, compare it. This is again a small tree, but if you have, assume you have 3 here, 3 more here, or 4 more here, right? If you have like this structure, still it becomes complex. Now, to one alternative way to reduce the, we know the alternative for BST or any binary tree or AVL tree can be B tree. Why? In all these 3 logic is same, height problem is there. We are having the height increases when the number of elements increases, right? And the complexity performance also decreases. Complexity increases, performance decreases. That is why we are talking about B tree. In B tree, the advantage is the height has come down. Each node is storing more number of elements. But again, still insertion deletion, they are little problematic even in B tree. That's why we have come up with a new tree called B plus tree. In B plus tree, what will happen? You know, all the elements will be available only in the leaf node, only at the leaf level. The elements will be available only at the leaf level. All its roots will contain only those pointers. They will contain only the pointers. Elements are available at the leaf nodes. Meaning, if I draw a B tree logic, okay, if I draw a B plus tree, I will have a element here. Okay, it will not contain anything. It will contain 2 pointers, left and right child pointer, like this. Again, this will contain a left, middle, and a right. Left, a middle, and a right. This is same as your B tree, you know. But the elements will not be here. These 3 nodes will contain only the links or the pointers. Okay, like this. If I draw it more specifically, it is something like this. So, this contains 3 elements. This contains again 3 elements. Okay, this will contain the pointer about this node, which contains 1, 2, and 3. This will contain a pointer with 4, 5, and 6. This will contain 7, 8, and 9. So, there are no elements in the internal nodes. Only leaf node contains the actual elements or keys in our language here. Okay, the internal nodes will not contain any element. All the elements will be available at the leaf node. See this example here. See, the elements are here 2, 3, 4, 5, 10. Okay, what is there here? This 4 means this 3 is holding the pointer of this and 4. Okay, these are not the elements, these are just pointers. The elements are at the leaf node only. Okay, see, the B plus tree is similar to B tree in that it is a tree structure with a fixed number of keys per node. We know that, no? B tree has fixed number of keys. How? If somebody tells you level 1, I will have one element. If I say level 2, I will have two elements each. If I say level 3, I will have three elements each. This is fixed. Okay, and it is balanced, so that all leaf nodes are at same level, it is balanced. Whereas, however, in B plus tree, all keys are stored in leaf nodes, while the internal nodes only contain pointer to other nodes. They contain pointer to other nodes. So, these will contain only the pointers. Elements are there here. The actual elements are 2, 3, 4, 5 and 10 in that tree. Okay. All keys are stored in the leaf nodes here. Okay. While the internal nodes other than leaf, everything is called an internal node, only contain pointers to the other nodes. Pointers to the other nodes like this. This is a pointer, this is a pointer, this is a pointer, this is a pointer. We are storing pointers, right? This is your B plus tree. What are the different characteristics? Let's study this more in detail. B plus tree. First characteristics is balanced. Like a B tree, B plus is also a balanced tree, meaning all the leaves are at same level. Next, multiple keys per node. This is also same like your B tree. B plus tree allows multiple keys to be stored in each node. Even in B tree, we are doing that, no? We are storing 3 keys, 2 keys. Multiple keys are possible even in B plus tree. Ordered, it maintains the order of the keys. That's what same as your B tree. We are maintaining order of the elements. They are in sorted order, which makes searching very efficient. Next, all keys are stored in leaf nodes only. Okay, in B plus tree, all keys are stored in leaf nodes only, while the internal nodes only contain pointers to other nodes. They contain only the elements are there only at the leaf nodes. Okay. Next, internal nodes have a higher fan out. Okay. Maybe I don't know whether you have studied this fan out, fan in operating system, right? Fan out means it is something linked with the performance. Okay. The internal nodes have a higher fan out, meaning accessing the nodes is very quick and faster. Because the internal node only contains pointer to other nodes, they can have a higher fan out in a B tree than a B tree. The internal nodes, there is only pointer, so there is no element. So, fan out means accessing element is not required, it is very faster. This allows more efficient to use memory and faster data retrieval. Okay. Fan out, fan in are concepts in operating system. So, they are linked with the performance parameter of the particular component. Okay. Next, where do we use this B plus tree? Very important. See this. This is what B plus tree are actually used in your RDBMS. Okay, in your structured query, the SQL part, we are using B plus trees. How? Database indexing. I think you are aware of creating index for a table, right? If there are columns A, B, C, D, E in a table, you can make A as index column. Why index? Because searching is very easy with respect to index, right? So, B plus trees are commonly used to index large databases. The keys in the B plus tree are the values in the indexed column. The leaf nodes of B plus tree contain pointers to the actual data rows of the table. Meaning, I will explain this point. See, you are having a table with you. A table is there which contains the columns A, B, C, D and E. The keys in the B plus tree are the values in the indexed column of the database table. This values, no, maybe it contains 1, 2, 3, 4, 5 as the values. They are there in the keys, and the leaf nodes of B plus tree contain pointers to the actual data rows. So, one contains the access to this data B, C, D, E values. 2 contains the access to this data. Okay, same again B, C, D, E values. Like that it is stored. B plus trees are stored, right? It is used in database indexing. Okay, you are maintaining an index column, index variable. This index column or feature in the table contains some keys that are stored as the keys. Next, file systems. We also use them in file systems. B plus trees are used in file systems to organize and store large number of files. Okay, the keys in the B plus tree are the names of the file, and the leaf node contains pointer to the actual file data. Okay, they contain pointer to the actual file data. Okay, even in operating system, how we use in operating system, B plus trees are used to manage virtual memory, right. So when you study these different courses, now you will understand much better how to use this B plus tree in that context. Okay, now we can discuss that. When you study the advanced database, you will study about B plus tree. When you study file systems, you will study that. OS, you will study about B plus trees application. Even in networking, we use B plus tree. Okay, so different courses, as in you see different semesters, when you study different courses, you will be knowing the usage of B plus tree in those concepts. Okay, but widely B plus trees are used in database. Okay, they are used in database, right. So what are the advantages of this B plus tree? What are the advantages of this B plus tree? Right. So what are the different advantages of B plus tree? Right. We have also seen the advantages of B trees, right. So faster data retrieval because they have higher fan out. Okay, support for range queries, right. Why range queries? They can quickly retrieve a range of data from the tree. Okay, if you want from this example, maybe if I take this example even again, here assume there are no values here. If you want to get a range of values, you can easily get, because already we have arranged them in sorted order, right. That is also very easy in B plus tree. Sequential access is efficient. Why? Elements are in increasing order. See here in this 2, then 3, then 4, then 5, and then every element is in sequential order and increasing order. Okay. Balanced structure, like B tree, B plus are also balanced structure. Why? When it is balanced, it is very quick to access the elements. See, if you are having some tree as not balanced, okay, if you have a left skew tree, if you have, or a right skew tree you have, these are all not balanced. Accessing, always you will check this tree, it's left, it right, not there, again left, it right, not there, again left, right, not there. It's a problem. Instead of, if you balance it, it becomes very easy to access the elements, simply like this. Okay, so balancing tree is very, that's why even in BST we have no logic, but AVL tree, heap tree, we are all talking about balancing factor, right. So that's also one advantage of this B plus tree. Okay, it has wide application. Again, I will go back here in the database indexing. See, you are maintaining a table with you, you are having a table with you. In that table, there are some records, 5 features are there. There are some records of maybe student details are there. This is your roll number, this is your name, this is your marks, your class, your grade, your section, something I am maintaining here. Roll number, if I create index, okay, this index holds this entire value. This index holds the entire value. Okay, so we are maintaining a table here. This, let the table be student table. It will contain the index of 1, which contains the whole record of data. Then index 2, which contains the whole record of data, like this. 3, and this contains the whole record of data. Okay, this way we are trying to access the elements, right. So this is little information about B plus tree. So when you study the advanced concept like advanced DBMS or operating system, you will learn more about the application of these B plus trees in real time or in other courses of computer science.